In this video, we're going to be taking a look at the derivative graphs of our trigonometric functions. That means that I'm going to be taking a look at the gradient of my functions. If I had put a tangent to my function, where would it have had an increasing gradient, a decreasing gradient, or in fact, a zero gradient? Taking a look first at the sine x function, let's take a look and see what its gradient looks like. From 0 all the way up to pi over 2, I have an increasing gradient. Exactly at pi over 2, I've got a 0 gradient. Then my gradient decreases all the way till when x is 3 pi all over 2, where once again I have a 0 gradient. And lastly, my gradient is increasing from 3 pi over 2 up until 2 pi. Also, in addition to this, I have a change in concavity, and this happens exactly when x is pi. Let's see what this looks like if I draw the derivative function of sine of x. Remember, the derivative function is the function that describes the gradient of my function. We said that we had two zero gradients, and those were exactly when x was pi over 2 or 3 pi over 2. We also said that we had a concavity change, and that was when x was pi, and that's reflected as a turning point on the derivative function. On my derivative function, the y values show me the gradient. If I have a plus y value, then that's going to be an increasing gradient, and a negative y value depicts a decreasing gradient. On my function, I said that I had an increasing gradient from 0 to pi over 2, and so I must make sure that for the increasing gradient, I draw my curve above the x-axis over here. Then my graph had a decreasing gradient. For a decreasing gradient, I need to have a negative y value, and this happened over here. And lastly, after 3 pi all over 2, where I'd had a 0 gradient, my graph once again has an increasing gradient for the last part of my curve up until pi over 2. You should be able to notice that the derivative function of the sine x function is in fact cos of x. Let's try the same trick with the cos of x function. Taking a look at the cos of x function, it decreases all the way down from 0 to when x is pi. It has a 0 gradient when x is pi, and then it has an increasing gradient. In addition, you should notice that it also has a 0 gradient when x is 0 and when x is 2 pi. Lastly, we must notice where we have concavity changes, and I have two concavity changes. The first one is when x is pi over 2, and the second concavity change is at 3 pi all over 2. If I reflect the gradient information of the cosine function, it's going to look as follows. I said that my gradient function had three zeros, when x was 0, when x was pi, and when x was 2 pi. I also said that I had two concavity changes, and they are reflected as turning points on my derivative function. The cosine function decreases and then increases. If it decreases, then I have to show that as a negative y value on the derivative function, and that is why I've drawn it below the x-axis. Then, after pi, it has an increasing gradient, and that is reflected with a positive y value on the derivative function, represented over here. I've shown you graphically how you could find both the sine x derivative graph, which was cos x, and the cos x derivative function, which is minus sine x. Let's look at another way that I could have found the cos x derivative function. If I take a look at cos of x, I could have written it as sine of pi over 2 minus x, using your complementary functions. In sine pi over 2 minus x, I actually have two functions. It's a composite function where the outer function f is going to be equal to the function of sine of x, and g is going to be the function of pi over 2 minus x. If I have a composite function, then I can find the derivative using the chain rule. Remember, when I do the chain rule, I find the derivative of the outer function, and I times it by the derivative of the inner function. So the derivative in the variable x of cos of x is in fact going to be the derivative of f, and that is going to be the derivative of sine of x, which we've just discovered is cos of x, all times by the derivative of the inner function, which is just minus 1. In other words, the derivative of the cosine graph we discovered is going to be minus cos of pi over 2 minus x. If I reduce cos pi over 2 minus x once again, I can write that as sine of x. In other words, the derivative of cos of x is minus sine of x. And that we could see very nicely going back and looking at our curve. In our next example, we're going to take a look at the derivative of tan of x. Now we know that tan of x is actually sine of x all over cos of x. Well, if I've got a numerator and a denominator, and I want to find the derivative of that function, I'm going to have to use the quotient rule. So using the quotient rule, the derivative of tan of x is going to be the following. It's the derivative of the top function, and the top function I'm going to call f. The bottom function I'll call g. The derivative of sine of x is cos of x, times that by the bottom function g, which is cos of x. Then minus the derivative of the bottom function, and we now know that that is minus sine of x, and you times that by your top function, which is sine of x. And that must all be written over the bottom function. Let's do that in black. The bottom function, which was cos of x, all squared. I'm going to continue by simplifying this expression. And so the derivative of tan of x is actually going to be cos squared of x plus sine squared of x, and that is still all over cos x all squared, which I'm going to write as cos squared x. Using our square identity, we know that cos squared x plus sine squared x is 1. And so I can write the derivative of tan of x as 1 over cos squared of x. Well, we know that cos squared x has got a reciprocal, and so instead of writing 1 over cos squared of x, I could have written the derivative of tan of x as sec squared of x, sec squared x. We've now investigated the derivative functions for sine of x, which is cos x, of cos of x, which is minus sine x, and the derivative function for tan x, which is going to be sec squared x. If you change cosec of x to 1 over sine of x and use your quotient rule, you can find the derivative of cosec x, and that will come to minus cosec x cot x. And similarly, you can find the derivative of sec of x, which is the derivative of 1 over cos x, and the derivative of cot of x, which is the derivative of cos of x over sine of x. I want you to practice these now to see if you can do them. Once you have, fortunately, you'll be able to consult the following table because all your trigonometric derivatives are given to you in a table in AP Maths. You don't need to memorize this table, but it is very valuable for you to know where these derivatives actually came from. And you have now very cleverly worked them all out, either graphically or using your quotient rule or your chain rule.